Okay, very good. Thank you. Well, in my introductory presentation this morning, I mentioned that, one of the value propositions of numerical simulation is the ability to explore simulation parameter or ground motion and infrastructure response parameter space in a way that may not be supportable by sparse observational data. So in the next few minutes, I'm going to show you an example of a evaluation and study of the influence of rupture velocity on both ground motion and building response. And this was really motivated by the observations from the Turkey earthquake. As many of you know, that was identified as a near shear or super shear rupture through many segments of the fault with very, very large directivity and fling step components with over 200 kilometers of the fault. So this looks at a very important parameter, and we need to understand it in more depth. And so we've been through a parametric study I'm going to share with you. I want to acknowledge my co-workers, Hujun Tang and Junfei Wang from Lawrence Berkeley National Laboratory, and Armin Pitarka of Lawrence Livermore National Laboratory that is supplying our rupture models for this evaluation. And I want to start this notion of near-field motions by going back to 1966, because I think there was an interesting question posed in the BSSA paper by Hausner and Trifunic. And they observed in an array, seismic array that crossed the San Andreas Fault there, station number 2, which has kind of become a famous record. They observed in the fault normal motions there, and I'm actually showing the data, they observed a double-sided velocity pulse and a very large, relatively large for the motions, fault normal directivity pulse. And there was a lot of speculation about that at the time. Certain people thought the instrumentations were messed up, and there was erroneous data. But as we know today, that was a real phenomenon. And I just wanted to draw your attention to some of the dialogue in that paper. And if you haven't looked at that paper, it would be really informative to read it. And I've highlighted it in red. This raises the question as to the possibility of a magnitude 6.5 or 7.5 shock generating an even larger pulse. And although they said that, they tended to think that that was probably not very common in that paper. And so, 57 years later, we're sort of getting an answer to how large these fault normal pulses and directivity fling steps can be. And so I'm showing you some data from the Turkish earthquake. This is data that was shared by Hasada. He processed these records to remove the velocity trend and thereby get estimates of the full broadband with permanent displacement. And you can see at site 2718, the velocity, double-sided pulse, and a fault normal pulse, and then the fault parallel, a large fling step. You go all the way down, farther down the fault, see something very similar with this very, very large fault normal pulse. And I just draw your attention to the fact that this is essentially 10 seconds in duration, and then the rise time on the fling step. And so we set about taking a look and doing some analysis of these motions for Turkey. And I'm just going to show you some comparative pulses here. And this really goes to the heart of the question that Hausner and Trifunic had raised. Here's the Parkfield pulse to scale. It was about 25 centimeters. This is some of our simulations, fault normal pulses for the Hayward fault with the high rupture velocity. I'm going to get into that in a moment. And then we're showing the Turkey pulses here that are extremely large. And if you go down to this particular site, you can sort of see the answer to the question that Hausner and Trifunic sort of posed. This is 0.25, 0.7, 2.5 meters. So the amplitude of this pulse is essentially an order of magnitude larger than an observation from the earthquake in Parkfield back in 1966. So we began to look at these motions in a little more detail because we wanted to understand what they looked like before we got into our simulation space. So I'm showing you there were sort of two populations of these records. One population that had a fault normal pulse that is sort of a single pulse, like you see here. So if you high pass filter that, you still see that single pulse in both of these records at these sites. However, there were places where there was a double pulse embedded in the single pulse. And so this station that I alluded to, a couple of these already, if you do a high pass filter, that big, long, giant 10-second pulse sort of disappears, and you see two pulses, which in fact, for many structures are more relevant to the structural response, as I'll show you in a moment. And so this is an interesting flavor, and we decided to explore these things and see if we made observations of this in our simulations for the Hayward Fault database. I'm just going to show you a couple quick examples of the billing response. We really like to plot the billing response in terms of absolute displacements. This is a nonlinear analysis of a 20-story steel moment frame designed for a highly seismic area. And you can see the motion here hits that pulse, and you can see the building is thrust over. But if you inspect this very carefully, you see the damage. A lot of the damage is caused by this secondary pulse. And so the building is not responding to a single pulse. It's having rigid body motion, as you can see here. We're plotting absolute displacement space. The building moves over due to that 10-second very, very large pulse, but the subpulses that are hidden within, if you will, are really the things that are causing the damage to that building. So it's a little more complicated than just a single fault normal pulse. This is another example of a 40-story building at another site, TK3144. You can see here comes the fling step coming up that moves the ground very rapidly. There's a high velocity here, as you can see, 2 meters per second. The base of the building moves over very fast. The building can't keep up with it, so it puts a snap into the building and propagates a wave up the building that actually damages high up in the structure. So these are some of the characteristics that we observed by looking at real data. So we really wanted to understand, given the fact that this was a near shear or super shear event, we really wanted to develop a more comprehensive understanding of the ground motion response and the infrastructure response as a function of the rupture velocity. And we would probably be waiting a gazillion years to try to get consistent data for a given site that explores this variation. So what we did is we took the EQ-SIM framework, going all the way from generating ground motions to structural response. We looked at a suite of 5 different rupture velocities, starting with 0.6 and going up to 1.05. And then we used these canonical nonlinear steel moment frame, very detailed fiber model buildings. And these are based on a design done by Hassan Astani for some buildings in the Bay Area. And we went about trying to understand how this velocity variation it affects both the ground motions and the structural response. We used the Graves-Pitarka kinematic rupture model, like we've done so much and so often in our evaluations for the simulated ground motion database, only we used it in a slightly different mode. They have developed an option based on a 1D velocity structure idealization to develop variable and target velocities of rupture throughout the entire rupture plane. So we invoke that. So for example, for a 0.8 V sub S rupture, in other words, the velocity of rupture, 80% of the V sub S velocity, you can see the sort of distributions they're getting with a median value that is very close to the target value. So that's for 0.8, and this is, for example, for 1.05. And so it's realistic because there's variability of velocity as you go along this fault, so you just don't have a single rupture velocity everywhere, but you can tune this to get a median rupture at your target velocity to explore this parameter space. What we see immediately when we start to look at the ground motions, it's very clear that the rupture velocity has a profound effect on the velocities. I'm showing you a rupture. These contours are showing the amplitude of the velocity vector. For 0.6 V sub S and 0.95 V sub S, you can just see with your mind's eye how much more intense this is, both in terms of the directivity effect and the amplitude, much, much hotter. And if you look here at plotting the velocities, the contours of those velocities, you can see the high velocity rupture has much, much higher ground velocities that are associated with a higher velocity rupture. So let's look at systematically what happens at a site. And I'm going to look at this site here for a northern hypocenter rupture, one at the far end where you get directivity buildup. I'm showing you the motions at that site, the waveforms, going a velocity of rupture from 0.6 all the way up to 1.05. What do we see? I think it's most instructive to look at the velocity and the displacements. You can see as the velocity of rupture increases, we start to get this very coherent, sharp, high amplitude displacement pulse emerging that continues to monotonically increase in amplitude and shortening of duration as we get higher and higher with the velocity of rupture, and that rupture front becomes more compressed. And I'll show you an example of why that is in just a moment. This is the velocity. Also, pulse gets much, much larger. Some of these, the acceleration doesn't grow that much. It does a little bit here, but if you look at the fault parallel, there's almost, very little growth in acceleration with their higher rupture velocity. But what we see here now, in terms of the fling step, at the low velocity of rupture, it's a very long, slow, relatively slow rise time to that peak displacement. As we increase the velocity of rupture, that rise time shortens because the velocity is higher and you're integrating a large velocity pulse. So it shortens and the amplitude gets larger. So that characterizes how these ground motions affect the characteristics of the motion at that site. We really didn't, it was hard for us to envision how those sharp pulses were being generated. So we took our 2D model and we began to look at what the global transverse displacement of the ground looks like in this rupture characteristic. So what you see here is you get this very relatively long displacement blob that is emanating from the rupture and propagating down along that fault. And you can see that as we increase the rupture velocity, that pulse gets shorter and sharper. So if we now correlate that 2D solution with looking at the ground motions at each site, I think you'll clearly see how these large velocity pulses emerge. Here comes the blob, and that's 10 to 15 kilometers long, and you see the ground motions at this site. And because this velocity is faster, the blob is moving faster, and it gives you a faster rise time and a shorter duration, but a higher amplitude. Moreover, what we see, and I'll show you this analysis in a minute, you see the beginning of a double pulse here versus a single pulse here. So not only do we see that consistently in a lot of the Turkey motions, we see that consistently in our simulations. And let's look at what that's due to. So let's go in and look at the motions here where we see this doublet. You can see when we high pass, you get these double pulses of motion here. So here comes the lobe of displacement. I'm showing time snapshots. As that lobe gets close to this site, you see a bit of a bifurcation due to the effect of the geology and the rupture model, and it's no longer one moving lobe, it's two moving lobes. And that two lobes is exactly what leads to giving this a double pulse at that particular station. Contrast that with the high rupture velocity, where everything looks pretty monotonic. At another station, rather, not with the same rupture velocity, other station, you see this single pulse. When you band past that, still preserves sort of a single pulse, and you don't see at this particular site that double bulb with two lobes of the passing displacement field. So this gives us some insight as to exactly what we're seeing in those motions that significantly affect the response of the structure by generating these double pulses. If you go into the engineering response now, thinking about the building response and the implications for building response, you can gain some insight by looking at the velocity spectra as a result of this rupture at different velocities. What I'm showing you here is the velocity response spectra at the red sites and the blue sites for a rupture velocity of 0.6 v sub s. I'm superimposing on that 10 Turkey sites, the velocity spectra, as well as Hesada's median or average. It's an average of the velocity spectra at a large number of sites all along the Turkey fault. What you see is when our velocity of rupture is low, we fall off quite a bit in the long period in the velocity response spectra. When the velocity is high, look what happens. Wow. Particularly down here at this directivity site, fault normal, you get a significant increase from 1.5 seconds on in your spectral ordinance. And also, even at mid-fault, you see that increase, although the directivity effect is not as pronounced here. So what does this look like? This looks like concern about the implications of these motions for larger period systems, i.e. above 1.5 seconds. So what we did next to really nail this down is we went into and did our full end-to-end EQ sim evaluations. We took all four of those building models and we analyzed them at every site within the domain for both fault normal and fault parallel motions for different velocities. And what we did is we took two velocities. We looked at a velocity of rupture of 95% v sub s and a velocity of rupture of 60% v sub s. And we got the building drift ratios for each of those, and we took that ratio. So what you're seeing here is a plot of the contours that exactly demonstrates that ratio. So anything above 1.0, referring to an increase in the PID as a result of that increase in velocity, you can see it's quite large distribution. This is a 3-story, and I'll say straight away that the number of sites that have a tremendous increase for the 3-story is not pronounced. The 3-story is a short period structure, so you don't see that pronounced of an effect. As you get into the 9-story, you begin to immediately see a couple of things. You begin to see increased basin effect as a result of that high velocity of rupture, and you begin to see a significantly increased directivity effect. So now, if we look at that PID ratio of the building response at a high velocity rupture to the building response at a low velocity rupture, you begin to see the growth of these large increases here. And so at this case, almost 90% of the buildings throughout the entire domain have an increase in the PID of that building. About 20% have an increase of 2x or more. And if you delve into this, some local locations have a very large increase in that ratio. So you can really begin to see the influence and the effects of this high velocity rupture on the building response. 20-story building, very similar. This is the Livermore Basin here. So you begin to see basin effects increase in addition to the directivity effects. And again, we see here almost 20% of the buildings in this domain for 20-story buildings have a 2x or more increase in peak interstory drift. You see that effect here, both fault normal and fault parallel, interestingly. And then for the 40-story, you really begin to see the effect of the velocity on basin response. This is the Livermore Basin. You really begin to get resonance and wave trapping in that basin as a result of the increased velocity going up to 0.95 v sub s relative to the 0.6. And now we see that almost 18 and 23% of the buildings throughout the entire domain have an increase of at least a factor of 2 in building peak interstory drift. So the bottom line is that if you look at these plots summarized, fault parallel motions, this is the increase in response to the percent of buildings throughout the entire domain that have an increase of greater than 2x. You see the 9, 20, and 40-story buildings kind of track, and there's a much larger increase in the interstory drift relative to the short period building. Same thing with the fault normal. Here's the fault normal. You see that these buildings, 9, 20, and 40, have a tremendous increase in sites where you have a 2x compared to this. Interestingly enough, we didn't exactly expect this, but you see that the trends in the fault normal and fault parallel are very, very similar. There's a lot of discussion and I think a predominance that the fault normal motions tend to be more dominant in terms of damage. This indicates not necessarily so. We have to look at this a little more carefully. So let me try to summarize in the takeaways. So retrospectively, we're understanding now that these large strike slip earthquakes over the past 15 years, as a matter of fact, 14 of 39 in this study, which was very nicely done and characterized here, have exhibited characteristics of super shear rupture. These events are not rare. That could be the conclusion of that. And so the question arises, is that an engineering community, how should these be incorporated in our ground motion hazard evaluations as well as in our structural response? Number 2, high velocity rupture events can significantly increase regional risk to infrastructure, particularly for longer period systems, for example, mid to high rise buildings or long span bridges. Better geophysical understanding of the conditions under which high velocity ruptures occur can help constrain the risk associated with these highly destructive events. There's speculation that strike slip faults can be particularly generative of these types of things, but more research from the earth science community needs to come in here to help constrain these. And then finally, one of our takeaway lessons is our entire velocity rupture utilized in our first 50 realizations was 0.72% of the shear wave velocity. We have stepped back and we have actually gone through and we're adding a bunch of more realizations at 0.9 and 1.0 v sub s to try to fill out that. And so this was simply an oversight as we went into this database development due to our lack of understanding of the significance of these motions when we got started. But simulation is helping us inform and improve that as we move forward. And I think I'm out of time.